Yes. Yes. Check the mic also. Okay. They're not audible online. Good if microphone is on. Yes. Mhm. Hello, can you hear me? Yes. Okay. Okay. Yes. Yes. Uh, oh, okay. Hello. Speak, speak. Yes. Hello, hello. Testing. Hope you can hear me. Hello, hello, hello. Hi, hi. Hello. Hi. Hello, hi. Hi. Also, I think. Okay. Yeah. I don't see the second down. Oh, okay. So we go. Yeah, it's a. Yeah, I don't know. Well, I don't think he minds that. I mean, it's nice, but that's. Yeah.
So that was in microphones here.
Okay.
They were muted. So yeah, I think it's either right now you're able to hear them, right? Yeah, so this one should be fine. It was most likely a wireless 2 or 3. Basically, what I did is there's another one of these in the AV room, and I just went in and unmuted everything. But it was one of these most likely that was just muted. I don't know who did that, but it's just something to check beforehand. Yeah. Yeah. Okay.
Good.
Yep.
Hi. Hello. Hello. Can you hear me? Yes. Okay. Um, it's on. Hi. Hello. Can you hear me? Okay. Hello. Can you hear me? Hi. Okay. Yeah. No, thank you. What's it up?
Your mic'd up?
Yes, I think we tested and the audio.
Okay, good. Excellent. West Bangalore?
West Bengal. It's Calcutta, the city of, yes, I grew up in Calcutta.
Bangalore is that.
No. So West Bengal is the state and Calcutta is the city.
Bengal?
Where is it's East India. Yes. So I did my undergrad in Bangalore. Like,
I
but
see.
yeah, before I came to Caltech, I was in Bangalore.
That's it.
But I grew up in Kolkata. Yeah, it's so funny because yeah, I mean, Mansi and I had an interesting experiences about the pronunciation of my name. The,
And what should I say?
the actual pronunciation, the correct pronunciation is Kishalay. The A's are pronounced, yes, the A's are pronounced as O's. But Mansi never agreed to go because it's pronounced differently in North India and East India. So even today, I just live with it. Guys, really, that impact told me that when the lunar trailblazer launch is right now, like coincident with this. Yes. So George told me that I want to come to your talk, but this thing is launching during your talk.
comparison.
Yes. Yes. I knew this was coming. Uh, usually this thing, talk start at 7 minutes past the hour. Is that still the thing?
7 minutes, no,
What's that?
maybe 2 or 3.
Oh, okay. I
Yeah.
thought so this thing was like people need 7 minutes to park their car outside.
That
Yeah, you
sounds like
see.
perfect time.
Yeah. Yes. Because MIT had the same thing, where every talk starts at the 5 minutes past because whatever it took people 5 minutes to go from one meeting to the next.
No, we'll be going a minute or two.
Yep.
Okay, let's get going. Thanks for coming today, everybody. Our speakers. Kishalay as many of you remember, Kishalay was a graduate student here. Worked on many different types of transients, all the way from infrared to X-ray. A lot of it focuses on X-ray, followed up with different types of transients. Been very productive. Just to demonstrate that, I want to show you the published content of his thesis. So I have many instances from Caltech students here. So here's a very nice one. Hunting for hidden explosions. Okay, several more. I won't go through all of them. Landscape of relativistic explosions. This is Anna Ho's thesis, so pretty excited about this. But Kishalay is going to this. You can see this like 2 or 3 times. A lot of concepts and a lot of good stuff. Because you work on many different topics, and since leaving Caltech, Kishalay went to MIT to do an Einstein fellowship. And just recently started at Columbia University as a professor. And worked on all kinds of things, planets, engulfments by stars, type 1A supernovae, 4 o'clock supernovae. It could tell us about black hole formation, all kinds of different things. So without further ado, take it away.
Thank you. Just so you know, I was at the right time at Caltech that both Getini IR and ZTF were being commissioned. So a lot of the pages in those theses are just spits images from ZTF printed onto the thesis. That's why it looks so thick. All right. So thank you very much for being here, and Jim for the introduction. It's a pleasure to be back. I think I've been having these back-to-back meetings, which is fun because I think I've kept in touch with the group here, but it's always nice to keep hearing updates on everything that's going on. So what I want to do for this talk is to give you sort of essentially tell you a bit about what I've been up to for the last 3 years since I graduated. And when I was making the slides for this talk, I also kind of realized that pretty much everything that I do was sort of set up at Caltech, like when I was a grad student here, and a lot of it, in terms of the stuff that I learned over here. And I was thinking about how to sort of frame this. And I realized that when I went back into my very, very old email, I found this. Yes. So this is a course that I took in my first year. You can see Lynn taught this course, Structure and Evolution of Stars. So by the way, Lynn, yes, Lynn, this course website is still up. Yeah, it's from fall of 2016. So yeah, yes. So this is a course that I took in my first year. And one of the things that I distinctly remember Lynn kept talking about is that you could be working on anything, exoplanets, cosmology, galaxies, doesn't matter what you work on, you have to understand stars. And I've really taken that to heart. And all of this thing that I do has to do with stars. And what this talk is going to be focused on is essentially this life cycle of stars. So I think a lot of the stuff that was covered in this course was about the life cycle of stars. If when you start with low mass stars, how they end their lives as white dwarfs. For more massive stars, they end their lives as supernovae, producing neutron stars and black holes. So what I want to convince you during this talk is that a lot of the stuff that I've been doing, which has been pushing time domain surveys in infrared light, they're essentially filling in gaps in the understanding essentially of nearly every step in this cycle that we sort of take for granted. And in some cases, giving us surprises because we are exploring a new waveband that hasn't been traditionally explored in the time domain. So to think of it, every single step in this life cycle involves some kind of an eruption that is particularly visible well in the infrared bands. And that's what this talk is going to be about. So again, not only was I learning about astrophysics, but I think one of the key things about being at Caltech was having fun with playing with instruments. And one instrument that I had a lot of fun with is this telescope called Getini IR, which hopefully many of you have seen at Palomar. It's one of the first wide field infrared surveyors where you're surveying the entire sky every couple of nights. Just to give you a sense of scale, this was about the entire visible sky every 2 nights in just J-band. So think of it as about 1/4 of 2 mass every night. The way we got it was by having very coarse pixels so that we could cover a very wide field over small number of exposures. And this itself, obviously led to a number of papers and discoveries that I won't get to time to talk about today. But again, the connection I want to make is the technical expertise, which is that I think during my PhD, I thought a lot about how to do things like this, which is image subtraction. The idea that if you take one image of the sky at one night, compare it to a previous one, and you subtract the two, every now and then you'll see a star that pops out. This is a star that has changed in brightness. And I spent a lot of my thesis just on trying to understand how do you do this most accurately? How do you calibrate images to make this happen day in and day out? So when I started as a postdoc at MIT, I was like, okay, so Getini was a fun project. We've made a number of discoveries, but what was the next frontier? Where could I take these techniques that I learned and apply it to something else and really push the frontiers of infrared time domain astronomy, even beyond what Getini IR was doing? And this is what really led to this project, which is we're essentially reimagining an existing telescope that's been around for more than 10 years way before even I was a grad student, which is this survey called WISE. So as many of you would know, WISE again has roots here at Caltech. The idea was that this telescope was launched in 2009. What it does is that it has this orbit around the Earth, and as it goes around the Earth, it has this very slow scan where every 6 months or so, it actually gets one full scan of the sky because it has this orbit that looks like this. It has this polar orbit. As the Earth goes around the sun, every 6 months or so, you get a full map of the infrared sky. So over the last 15 years, roughly, that NEOWISE operated, I think the traditional approach was that you take all of these NEOWISE images and you keep stacking them, get deeper and deeper and deeper, and find fainter and fainter sources, which is good, creating, finding more and more infrared sources. But sort of my idea was, instead of keeping adding things, why don't we start subtracting them and start finding things that change in brightness? And this is what that looks like. Essentially the same techniques that we do in Gatini IR, except you take WISE images. This is 2 WISE images separated about 10 years. When you subtract the two, visually it isn't as obvious, but you see that there is something that changed in a very dense galactic field. The same holds true for extragalactic fields. You have this, a galaxy that's sort of there. You wouldn't really say that it's changed in brightness, but as soon as you do image subtraction, you see that something has changed right in the center of a galaxy. That's the kind of power that image subtraction gives you. And what we did was that essentially I ran this similar pipeline on about 1 million images that WISE has ever taken over its 15-year survey. And immediately this popped out this sample of about 5 million variable and transient infrared sources that essentially had been overlooked in many ways, which are all there in WISE and just waiting to be mined. So that was the start of where all of these projects began. And what ensued was this huge program, which was a lot of work. We have this extensive ground-based follow-up program using national facilities, facilities through collaborators. And this is both in the ground, going from 3-meter class telescopes to 10-meter class telescopes, and also extending across the entire electromagnetic band, going from radio wavelengths, centimeter wavelengths to millimeter to all the way to hard X-rays. And that's really been the crux of making sense of this sample of 5 million infrared sources that we're dealing with. So all of this would not have been possible without this amazing group of people that I had the privilege to work with. Many of these people in the picture, but it's really been a mix of all the way from senior faculty to postdocs and undergrads who've worked with me on various aspects of these things. And a lot of the effort has come from doing detailed follow-up measurements on the data set that we've been collecting. So I'll try to highlight a lot of the work that's been done with my collaborators. All right. So I come back to this picture. This is going to be, you're going to see this picture again and again, because what I'm going to try to convince you is that these infrared surveys, the infrared explosions, are essentially teaching us new things about every single step in this life cycle. And the first thing, if you think of explosions, you probably think of supernovae. That's the most obvious one. And if you thought that infrared surveys have nothing more to teach us about supernovae than we already know from the optical, I'm going to try to prove you wrong, which is, I'll start with right over here, which is this question of, we sort of take this picture almost for granted. Okay, sure, there's a massive star that either turns into a neutron star or a black hole. But what I'm going to try to show you is how infrared surveys are, again, revealing completely new pictures in this direction. So to go into this point, I just want to start with this very simple question. And it turns out that doesn't have a straightforward answer, which is, if you ask this very simple question of what stars turn into neutron stars and what stars turn into black holes, is there a straightforward answer to that? In textbooks, they usually hear about things like a mass limit. Maybe things that are more massive than 20 solar masses turn into black holes. Less massive things do not turn into neutron stars with supernovae. But it turns out, this is sort of the picture that existed maybe 20 years ago. This is a plot from a review article from 2002 or 2003, which shows metallicity as a function of mass of the star and what we think its eventual fate is. The basic idea is that for low mass stars in this 9 to 20 solar mass range, most of these stars probably explode and successfully explode and produce supernovae. For stars that are more massive, they become so massive that at the time of core collapse, they are unable to essentially eject their outer layers, resulting in the fact that that most of these stars would end up as black holes instead of forming neutron stars. But this was sort of the traditional picture. If you ask supernova modelers, what this picture might look like in terms of more detailed simulations, this is what that looks like. It's not really these islands of explodability anymore. Instead, these look more like these picket fences where the green areas, these are masses, and the green areas indicate successful explosions, and the black areas indicate failed explosions, essentially things that form black holes. And you see it's a mess now. It's that if you look at simulations, stars as low mass as 12 solar masses might be turning into black holes, and it goes all across to 50 solar masses. And the main reason is that we really have no constraint on what this process looks like, especially when it comes to forming black holes. Because how black holes form and what stars form black holes is something difficult. And the reason for that is that the classical picture in terms of what a black hole formation event might look like is this idea that you have a red supergiant that has reached the end of its life. And as the core eventually burns up all the way up to iron, at some point it's unable to sustain itself anymore and it collapses inside into a black hole. Now, probably for very massive stars, this is the case that the outer envelope is not ejected, in which case what you expect is that the models have been to the effect that what you have is a central black hole that's powering a very low luminosity transients that illuminating this outer envelope that's barely bound. And this is remarkably difficult to detect. What you're looking at here is essentially a red supergiant that disappears without a successful supernova explosion. And in detecting individual stars at extragalactic distances that disappear, as you can imagine, is a remarkably difficult task to do. There is some precedent for this. This is probably previously the best well-studied event. This is a star in the galaxy NGC 6946, which was there in Hubble Space Telescope imaging from back in the 2000s. And then sometime around 2015, it was nowhere to be seen. It disappeared. And because of a survey that was being done with the large binocular telescope, there's this nice optical light curve that shows that over the last 10 years before it disappeared, sort of had this flat evolution, and then it showed a weak outburst for some time and then disappeared in optical light. And that was one of the most promising candidates that we knew of. But again, this requires extreme amounts of precision in that you have to detect individual stars at extragalactic distances, which is quite a challenge. It requires really the capabilities of HST and looking at galaxies at multiple epochs. But one of the classical predictions is almost on this picture. What you see here, these are optical light curves of this event. And what you see here are infrared light curves from Spitzer. You see that just before it decided to disappear, it had this weak brightening in the infrared, which we think comes from dust formation in this material that's surrounding the black hole, which is this material is cold. This material essentially is the outer layer of a red supergiant. And you would expect that even for very low energy shocks, this material would travel out and form dust. And this has been the prediction. And that's essentially the kind of phenomena we try to go out and look for. Look for low luminosity transients in nearby galaxies and look for events like this. So just to give you a sense, when I started this project, I think a lot of people were skeptical in the sense that, because NEOWISE has this 6-month cadence, whether do we actually see supernovae in the NEOWISE dataset? So just to convince you, yes, we do see supernovae. These are examples of all known supernovae that have been serendipitously observed in NEOWISE. So these are all nearby galaxies. You see when you do image subtraction, there are tons of these things that are just serendipitously observed in NEOWISE, even in the 6-month survey. And as far as this black hole story goes, it turns out I didn't have to look very far beyond this galaxy, which hopefully many of you, all of you know which galaxy this is. So beloved nearby Milky Way-like galaxy, M31. All right. So we had this program to go after luminous transients in nearby galaxies. We follow them up with ground-based spectroscopy, looking for all kinds of events. There could be stellar mergers, could be these types of low luminosity infrared transients. So in this particular case, this is one star that did something in M31. This is this star that we are talking about, this faint star in the middle that showed this brightening in M31. And if you look at what the archival images of this part of the sky look like, this is the same 3 stars that you see here. This is a ground-based near-infrared image. You see there is the same 3 stars. This is the star that showed some kind of a brightening surrounding around 2014, 2015 in that time period. So I was like, okay, let's go and get a spectrum of this star. I got some time on Keck, and we decided to go and take a spectrum of this star. And this is what I looked like when I went and pointed Keck at it. So you see that 1, 2, 3, these 3 stars, 1, 2, there's nothing else there. Star is gone. Now, thanks to Shri and Mansi, I had about 100 nights of observing experience on Palomar and Keck, and I knew that this was not common. Stars don't just disappear like that. And I remember this was like 2 or 3 in the morning. I was in Waimea observing for this particular night. I probably wasted about an hour on Keck trying to figure out what is going wrong over here? Like, is my finder chart off? What is this? So if you asked Percy, who was there at the night, this is probably what I look like at the time. It is shocking when you suddenly see a star that's been there for decades suddenly disappear in an image taken with the biggest telescope on the ground. So that really sort of started off this entire investigation of what's happening. Where did this star go? So fortunately, because this is M31, and there's other reasons to look at M31. There's a huge archival data set of this particular field. This is what the star looked like in HST images from about 15 years ago. I guess more like 10 to 15 years ago. So it's a huge infrared source. It's a very bright source. Like if it's detected from the ground, it's almost at the saturation level for HST. That's how bright it is. So it's a luminous star in M31. And sometime around 2015, 2016, this is what the long-term 15-year light curve of this object looks like in WISE and other optical bands. This infrared, so these squares are the WISE light curve, again, sampled at 6-month cadence. So it's not great cadence, but what you see is that there's this slow infrared brightening that peaks around 2018, and then it disappears. This is what we essentially caught in the pipeline, this slow infrared brightening. But what it does in the optical is even more remarkable in that just plummets. This disappears, is covered with PTF, ZTF, PAMS, exquisite coverage, and they all say the same story. The star just disappeared somewhere around 2018. And we confirm that because, again, this is M31. HST just keeps staring at it. And if you look at images from 2022, the same field, exact same field, this star, nothing. Not even detected in HST. That's how remarkably faint it became in the optical bands and similarly in the infrared bands. So, you can almost start to guess where the story is going, but I just want to take a moment and sort of, this was a shock for us. Like a luminous massive star in M31 disappeared over the last decade and nobody batted an eye. This was quite the shock for us at the time, and it really motivated a huge range of investigations that followed on this source after that. So I want to walk you through some of those steps, what we think is going on, and why this might be very key to understanding how black holes form, stellar mass black holes form from massive stars. So what we can do is simple exercises. We can look at what the SED of the progenitor looks like. This appears to be a luminous massive star. This is just the raw data from HST and Spitzer. Again, M31. See, it's a fairly luminous star, 10 to the 5 solar luminosities. One of the key things is that there's this clearly a stellar spectrum over here, and there's a mid-infrared excess. To explain that, you need a dust shell around the star. This is what the dust shell model looks like. You have the star in the optical and a dust shell that surrounds it in the infrared. And you can ask, where does this land in the HR diagram? Again, it's fairly simple exercise, log L, log T. You see that it lands somewhere very close to the end stage of what a massive star might look like. It sort of falls on these are single star tracks for what a star does at the end of its life. And you see it falls right on the 18 solar mass track, but with the caveat that its position is not really in what you would call a traditional red supergiant. It's bluer than that. It's hotter than a red supergiant. And normally, if you saw this star in another galaxy, you would call it a yellow supergiant because just hotter, massive star. So, what this hotter temperature essentially means is that instead of being a massive hydrogen envelope around the star, what you have is a star that has lost some of its upper hydrogen envelope. And just to give you a sense of what that picture looks like, imagine a helium core, a massive helium core from a massive star with a thin hydrogen envelope around it. We think it's a few tenths of a solar mass. It's a yellow supergiant that's surrounded by a dust shell. And by running more careful models by including enhanced mass loss, can show that you can explain these types of properties with a star that initially started with about 20 solar masses and then ended up with about 5 to 7 solar masses, depending on how you treat the mass loss. But the main point being that this is a massive star that has lost a lot of its hydrogen envelope. And if you ask what did it do during this remarkable fading, it essentially went from being this luminous massive star that very luminous in the optical to being a source that is essentially fair amount of infrared light, but it's still bolometrically fainter than the progenitor star itself, and almost nothing there in the optical. And you can essentially, again, do your same model fitting to show that the luminosity today is it's fading, and it's continues to fade to less than 10% of what the massive star used to be. There is no evidence for any explosive outburst from the star itself. The optical sort of quietly disappeared. Evidence of definitely no supernova and not even like a low energy transient at all. And for some reason, it has continued to slowly enshroud itself in dust. So, one of the only ways we could really come up with to explain why did a massive star suddenly turn off its central energy source. It's almost like there's this star that was happily burning away its fuel, and suddenly something switched it off in the center, and it continues to fade to less than 10% of its projected luminosity. And one way to, well, I think the most promising way to explain that is this idea that if a star collapses into a black hole in its center, eventually this material falls back into the black hole. But the reason why it continues to produce emission is because this material cannot fall back immediately because of the angular momentum in the outer envelope of the star. These yellow supergiants have convective envelopes. Convection has a lot of angular momentum, and that prevents the fallback of the material directly into the black hole. And what that does is that instead of the star just randomly disappearing, what we see is if you plot the luminosity as a function of time, is roughly constant for the first 1,000 days before it starts plummeting below. This initial constant phase is quite important because what it shows us is that the luminosity is capped at very close to what the Eddington luminosity for a 5 solar mass black hole would be. It's almost exactly the same as a Eddington luminosity. And the idea is that as this material tries to fall back in, most of it is actually ejected out because it can't fall back in because of the angular momentum in the envelope. And we can actually run some models to show that if you injected some amount of energy, roughly of the order of 10 to the 47, 10 to the 48 ergs, you see that these models line right up. The idea is that initially the fallback rate is very high into the central black hole, but the luminosity doesn't exceed what the Eddington luminosity of the black hole is. So essentially constant for the first 1,000 days. But as soon as the material accretion rate drops low enough, it starts tracking the mass accretion rate onto the black hole, and this sort of log linear decline in the luminosity. All right. Yes. So this has been definitely one of the most interesting objects that has come out of this project. But I want to move on to sort of other aspects of what we are finding. So I talked about the end stages of massive stars and how they might end their lives. Let's think a bit about what happens to stars just before they explode. In that, one of the key things that we know of today is this idea that massive stars in particular lose a lot of mass just before they die. And when and where this mass loss takes place, we see some evidence for that in supernova observations, and some of it is predicted theoretically, but really pushing that envelope of understanding how frequently do massive stars lose mass, and at what time before the supernova actually happens is something that's at the forefront of what we try to do in supernova physics. The idea is that we can see evidence for mass loss from massive stars in the supernovae that they produce. So imagine if you had a massive star that was about to explode with some recent episode of intense mass loss. This is essentially what we would look like. So the cartoon picture, the idea is that you have a star that's surrounded with some dense circumstellar medium. And usually the way you infer the presence of this dense circumstellar medium is that as this supernova explodes and crashes into the nearby CSM, you see signs of this interaction in the spectra of the supernova itself. So imagine if you had this material that's crashing into the nearby CSM, this material is heating the gas. And as it does that, it produces all kinds of spectroscopic signatures. I know today now there's a zoo of things. There's type 2Ns, 1BNs, 1CNs. There's an entire zoo of things that we think come from these supernovae interacting with nearby dense shells. But one key thing is that the only reason we see supernovae interacting with dense shells is because this material is interacting with the shell by the time we actually observe the supernova. In the sense that imagine if you had a shell, imagine if you had a shell that was not entirely close to the star, but very far away. This is material that's been ejected maybe 1,000 years before the explosion. And this is stuff that's regularly predicted in theoretical models. Jim and Samantha here have models of these intense mass loss episodes that happen just before core collapse. But in this sense, not the years before, but in the thousands of years before the explosion. In that case, you would actually, by the time the supernova actually reaches the diameter of the shell, you're not usually observing these supernovae anyway, in that, because it would take the supernova of the order of 1,000 days to even reach the diameter of the shell, so that usually these are not phases in which supernovae are followed up with spectroscopy. But what we've been trying to do essentially is use this idea that even if you have a shell of material that's interacting, a classical prediction is that this shell forms dust. And this dust can be heated by the shock itself, so much so that even if you don't have a spectrum of the source where at the time it's interacting, you can actually see the dust light up because of the interaction between the supernova ejector and the shell. And NEOWISE, because essentially gives you free data in the sense you get free infrared data for every point in the sky. You can use NEOWISE as a machine to search for how common these types of interaction episodes are. So this is again another aspect of the project that we are envisioning. This is the work that was led by an undergraduate student, Charlotte Myers, who is at MIT. And what Charlotte was doing is essentially looking at these transients in nearby galaxies, very similar to what we saw earlier. Again, the process is that we look at WISE images taken at one epoch, we subtract a reference, and then we try to look for things that change. And as part of this exercise, we find supernovae in these things. And what was remarkable about this one particular object is that it happened to be, if you just take the WISE light curve of this source and plot it on a phase-space diagram of luminosity, absolute magnitude as a function of phase. This is a luminous infrared source, happens to be one of the most luminous infrared supernovae that's ever been detected. You can see these stars are this object that we are talking about. And the only things that are comparable in luminosity to an event like this are these strongly interacting supernovae, which we think we have a good census of. But clearly, this was something that was less than 200 megaparsecs away, but was completely missed in optical searches, but clearly showed up in WISE as a luminous interacting supernova. So our program was, again, to go get follow-up. We had Keck time going after some of these events. I think I think Christopher probably took one of these LRIS spectra that we had. And when you go and look and take spectra of these things, you see that, boom, huge interaction lines. So what you're seeing here essentially is a supernova that was unnoticed. It's less than 200 megaparsecs away. It's a fairly, in the optical, it isn't as spectacular. But because it's interacting with CSM, it lights up in the infrared as this luminous infrared source. And we can confirm that the reason for this this luminosity is because it's interacting with the dense CSM shell that's nearby. And we can go back and dig more archival light curves of this. This is again, NEOWISE and ZTF light curves. What you see is that there's this huge infrared source that appears, no detections in NEOWISE, becomes very luminous. And there are very, very faint detections in ZTF that show that at that position, there was a faint optical supernova that was sort of never past a traditional cut for actually going after spectroscopy, but it shows up quite remarkably in the infrared bands. So these are upper limits. And then this is the infrared supernova that appears, this brightening in the mid-infrared. Yes. And the optical supernova is this. So you see there are non-detections up to about this time, and there's this faint optical counterpart. It's very faint, but it's there. Like we can confirm it that it's there in ZTF data. But this is a supernova that's less than 200 megaparsecs away. We think we have a complete census of supernovae within 200 megaparsecs, but there are definitely these low luminosity ones that that would be missed in a traditional core collapse supernova search, but you can find them with their luminous infrared emission that follows. So we can quantify how common these are. In fact, one of the key things we found this object was because the infrared emission is so much brighter than the optical band itself. And it turns out that if you do a more careful search of all ZTF detected supernovae, there is this population of things that show these late time infrared brightenings that far exceed what the energy output in the optical is. So what you see here, these are optical light curves of a bunch of core collapse supernovae that were selected for their bright mid-infrared emission. And at late times, you see there's this huge infrared brightening which comes from circumstellar interaction with a shell that is detached from the star. And we can now routinely confirm this with spectroscopy. These are, again, we go after some of these events, we get spectra, and lo and behold, these all show, these are essentially core collapse supernovae that do not show signs of interaction around the time of peak, but they transition into interacting supernovae a few months later. And this essentially points to a mechanism of mass loss which operates at timescales of 1,000 years before the explosion, as opposed to the few years that we see in other techniques where you probe really nearby material. So, and the number is, we can quantify this at of the order of a few % of core collapse supernovae do this. Yes. Yes. So what we can estimate is the amount of dust in the shell, and that's of the order of 10 to the minus 3 solar masses. So the associated gas mass would be like fraction of a solar mass, like 0.1 solar masses. Yes. So these are massive shells that are being ejected of the order of 1,000 years before explosion. And I think there's probably carbon burning episodes that happen of the order of 1,000 years before. So these signal essentially some sort of intense mass loss that happens coincident with these end stages of nuclear burning. But again, like this is something you would not traditionally find in an optical search because you wouldn't follow a supernova 1,000 days after the explosion traditionally. Yes. We don't know. So these are based just on WISE data. So it's just 2 photometry points. So it's difficult for us to tell what the composition is, but we have proposals to JWST to try to get spectra for some of these, but it turns out that the number for the mass doesn't really depend on it's not that sensitive to the assumed dust composition. So it may be a factor of a few, but the mass is of that in that order. All right. So I know we've been ignoring low mass stars, and I think there's this impression that low mass stars don't do anything fun, but I'm going to convince you otherwise. Low mass stars are fun, and they do all kinds of explosive things. And what I'm going to talk to you about is this phase where we think low mass stars turn from being red supergiants into these beautiful things that we call planetary nebulae. So hopefully all of us have seen some pictures of planetary nebulae. I think they're quite popular amongst even for amateur astronomers. So if you look at typical pictures of a planetary nebula, this is what that looks like. So one of the things that you ask is that if this picture of a single star evolution is correct, then clearly there's no reason for a planetary nebula to have these remarkable shapes that they have. As you can see, almost every planetary nebula that you look at have these shapes that are dumbbells and bipolar cones and all these kinds of exotic shapes that we see in planetary nebulae. So how do you explain that? How do you have these low mass stars if they were single? How do you do that? And the idea is that one of the easiest ways to make this happen is that if you had a star which was ending its life not as a single star, but as part of a binary system, you can imagine that these stars have companions that shape the outflow as the star ends its life, leading to these shapes. Now, what that looks like in practice essentially is that you have a star that's entering the envelope of a star that's dying. And traditionally, this is what is called a common envelope phase. And the way this looks like, we think, is this idea that they produce transients when they appear. This is a real Hubble Space Telescope time-lapse image of V838 Mon, which is a famous stellar merger in the Milky Way. And the idea is that as these mergers happen, there's this outflow that is ejected from the central object itself, so much so that if you follow the object in terms of spectra, it starts off being as this hot outburst that essentially looks like a K-type star, and eventually evolves into something that looks like a very cool star. So this is the same object observed a few months apart. It goes from being this hot star to being a very cool star. That's kind of the traditional way we find these things called luminous red novae. So they become very red over time as this material is ejected from the star. They develop these cold photospheres a few months after the outburst, and they remain dust enshrouded for many years after the outburst. And what that dust enshrouding does is that if you look at a light curve of what a luminous red nova looks like in our galaxy, this is what it looks. This is a luminous red nova in M31. It has this short optical outburst that lasts of the order of a couple of months. But the infrared emission that accompanies this dust that is produced in the expanding ejecta, this lasts for thousands of days. So it's essentially a purely infrared phenomenon in many ways, in that it's a very long-lived infrared light curve because of the dust that is formed in the event. So a few years ago, one of my colleagues, Morgan McLeod, who's at CFA, and I started thinking about this rather interesting problem in understanding the progenitors of luminous red novae. The idea was that we can now routinely find luminous red novae in optical surveys, and we can ask what do their progenitors look like, and ask where do they live on the HR diagram. So this is what an HR diagram of all the luminous red nova progenitors at the time look like. This is log L log T. What you see here, these white diamonds are all the known luminous red nova progenitors at the time. What you see here is something interesting, which is that even though most of the expansion of a star happens at the end of its life, right in this phase, the red giant and EGB phase, all of the luminous red novae that we see, which supposedly come from these common envelope events, we don't actually find any on the giant branch when the star is expanding the most. Most of these events happen in the phase where they're still relatively compact. And this is something that seems strange to us at the time. It's like, because really there should be more luminous red novae happening in this phase. And one of the ideas that we started asking is where are these common envelope events from these evolved giant stars? And Morgan came up with this neat idea that, because these evolved giant stars have these low gravitational potentials, they're very extended tenuous envelopes, maybe what happens is that as these companions enter the envelopes of these stars, even before the outburst, the final outburst actually happens, the thing gets completely enshrouded in dust. So much so that unlike the optical searches, which are good at finding optically unobscured events, these things would emerge as purely infrared transients that would be spectacular in infrared light, but not, you probably wouldn't even see them in the optical bands. So this is, again, another project that seems sort of nicely suited to what NEOWISE was able to do. NEOWISE is sensitive to very long timescale infrared phenomena that are luminous and potentially common nearby. So what we've been doing, and this is still work in progress, is identifying this population of mid-infrared transients that appear to occur only associated with giant stars in very, this is giant stars in the Milky Way and in nearby galaxies. The way that looks like is that these are two transients that, well, we have a sample of a few right now, but the idea is that we see these mid-infrared transients occurring coincident with stars that are clearly giant stars. One of them here is a galactic plane object right in the galactic plane. It's only 2 kiloparsecs away as far as we can tell. This is a similar object that's in a nearby galaxy that's only 3 megaparsecs away. And what we can tell is that these look exactly like red novae. What that means is that they show signs of dust formation. This is what a light curve of one of these galactic objects looks like. It's flat for some time, goes into this huge outburst. And we can see with some archival information that there's a faint optical outburst that accompanies the outburst. It goes into outburst at the same time, but then it suddenly disappears as it forms dust, but it stays on in infrared light. And this type of behavior is actually remarkably reminiscent of what we see in other red novae. But this is the same object, but overplotted with a old historical red nova that's known in the Milky Way. And you see that they all show these similar optical light curves that are roughly of the order of 1,000 days long. But the infrared light curve is a few thousand days long because it forms dust in the ejecta. And we've been doing spectroscopic follow-up for some of these. They have spectra that look, well, interesting for many reasons. These are spectra of 3 of such objects that we've identified. All the classic features that you see are these late-type molecular features that we see in red novae, molecules, water. This is a luminous red nova that is from an optical search. You see this remarkable similarities in the spectra. But what seems to be a key distinguishing feature of these things is that because these outflows are so cold, these cold outflows are unlike any normal stars that we see, is that when you zoom into these some of these spectra, you see evidence of these weird molecules that we don't see in any normal stars. Here is aluminum oxide, which is a molecule that, as far as I know, it's very rare in stars. But the only other eruptive objects that we know of where aluminum oxide appears is in red novae. So we can find these in the mid-infrared bands. We can follow them up with, to some extent, with near-infrared spectroscopy, and they show these classic signatures of red novae. They form dust. They show very cold photospheres. And if you, again, linking it back to sort of what I knew of at the time, is that if you ask where do these land in the landscape of infrared transients, this is a plot that I took from Jacob's thesis, where you see same luminosity as a function of time. All our objects that we find essentially land in this phase space. This population of objects has been historically called the sprites, which are these low luminosity, long-lived infrared transients that were previously identified in Spitzer surveys, but I think a lot of them were sufficiently far away. But these, because NEOWISE is good at detecting them in the galactic plane, we can do detailed follow-up and show that some of these objects might actually be these dusty common envelope events from giant stars, when stars really expand the most at the end of their lives. All right. So low-mass stars are fun. In case I haven't convinced you of that, let me go down that route a bit more and talk a bit about potentially something that is related to our own future as well. And that's something that's come out of this NEOWISE effort, which is this idea that what happens when small stars like the sun expand into a red giant, and what that means for the small things that exist around stars, and being namely planets. So I think it's fairly well established that architectures like this are common in the universe. I think it's fair to say that every star probably has of the order of one planet around it. And a classical prediction of this this entire stellar evolution scheme is that when stars evolve of the main sequence, as they become giants, these planets would get engulfed during the post-main sequence evolution. And if you think of the process of planetary engulfment itself, it's kind of like a stellar merger in that instead of a star entering the envelope of another star, you have a planet that enters the envelope of the star. And just because the planet is about 1,000 times less massive than a star, a binary companion, these objects would kind of look like red novae, but their energy scale would be much lower, probably of the order of 1,000 than compared to a normal stellar merger. So we've been doing this survey for transients in the galactic plane with NEOWISE, and that's where this particular object begins. You have this star, which is not particularly noticeable for any reason. This is the archival galactic plane image of a star from the Euclid hemisphere survey. And sometime around 2020, when I was still here, it showed this outburst in ZTF data. What you see here is nothing for as far as we can tell. Somewhere around 2020 showed an outburst, and then it fairly quickly faded away in the optical. It still looked a bit peculiar in many ways. But normally something like this, you wouldn't really notice in ZTF data because it's sort of another galactic plane transient amongst the thousands of them. But what was really striking about this is that once we started cross-matching ZTF data with NEOWISE, you see that there is this long-lived infrared afterglow that follows the event. And this is essentially, it almost sort of reminds you of this red nova phenomenon in that there's a short-lived optical outburst accompanied by a long-lived infrared afterglow. So we have spectroscopy of what this outburst looks like. Fortunately, we had one for this object, and we do all the modeling. And essentially what you're able to show is that this appears to be exactly an analog of what a red nova looks like, a common envelope event, except with an energy scale that's about 1,000 times lower than what we expect in stellar mergers, with the idea that the only way to explain the amount of energy radiated is that instead of a star engulfing another star, you have a star engulfing a planet. So this was a really cool animation that came out of this entire effort. What you see here is instead of this is a planet that's about to die. It's barely touching the surface of its star as it's evolving off the main sequence. And just before it's about to essentially get ingested by the star, it spews out this material because of the tidal interactions between the star and the planet. And at some point, the frictional forces are high enough that the planet essentially crashes into the star and produces this luminous optical outburst that we can see, followed by this long-lived infrared afterglow that we see in WISE data. So this was, as you can imagine, this is something that's probably relevant to us, our own future as a planet, because we live around a very average star that's eventually going to evolve into a red giant. So this got a lot of attention. This landed on the cover of Nature and I think somehow they managed to publish this article on May the 4th, the day of the Death Star, which is, I think it was, they were intentional about it. And it got a lot of, I think, fun press attention. And one of the things that I really had to try very hard to do is to convince people that this is not something we have to worry about right now. The sun is not going to engulf the Earth anytime soon. So I think that this was a really good demonstration of really attracting, teaching the public about how we do astronomy and how that relates to our own future as a planet. All right, so this is kind of all that I will go into in terms of detail. There's a lot of this stuff that's happened with the WISE project that I won't get time to talk about, all the way from supermassive black holes, TDEs, obscure TDEs in nearby galaxies, common envelope events with relation to type 1a supernovae, to X-ray binaries, the very end stages of stars, with black holes around low mass stars, and all the way up to young stars. Lynn has been remarkably helpful in helping me find the interesting object and and looking at the young stars as well. So there's this entire range of projects that I won't get to talk about, but please come and ask me questions if you're interested in any of this. But I want to spend the last minutes talking about where I think the future is and what I'm really excited about. So what's next? So one of the directions that I'm really excited about is this idea that Rubin will be a game changer when it comes to long red transients. So as we know, obviously this is the home of ZTF. Now I don't have to convince you that Rubin will never match the cadence of ZTF, but what it will be good at is looking at faint things and with distinctive color signatures because it has these remarkable 6 filters a time domain survey with 6 filters. So if you have any kind of a phenomenon that's long lived, so that don't worry about the cadence as much, and that has a color signature that is red that you can identify with a multicolor time series, then Rubin will be really good for that. And one of the directions I'm really excited about is looking for these planetary engulfment events with Rubin. So this is what the current Rubin cadence looks like. There are some patches of the galactic plane and bulge that are going to be covered at sufficiently high cadence. And you can ask what would a planetary engulfment look like in Rubin data, with the cadence that's been decided. This is what that looks like, this is a simulated, essentially you put the ZTF event out at 8 kiloparsecs behind 5 magnitudes of extinction. This is what it looks like. It's about 19th magnitude in I band, 24th magnitude in G band. It's very difficult to, like ZTF will not see this, but this is the kind of cadence we would get with Rubin. And what we would need to use, essentially the color signature, is that this is what the color evolution of this object looks like. It becomes fairly red over time. This is why it's a low luminosity red nova. And you can compare that with, let's say, other types of objects like classical novae or young star outbursts and so on. Unlike the other things that tend to either have constant colors or become bluer with time, these things, the red nova and associated objects, become redder with time, which I think is a key signature of dust formation in these types of outflows. So I know I hear from my colleagues that LSST will not be particularly useful for finding exoplanets because it's obviously not a transient survey. And I know that, I see this plot a lot of the, fairly often from my exoplanet colleagues, which is this, 100 times increase in the number of exoplanets in the last 25 years. But hear me out. Maybe the biggest contribution for LSST in exoplanets would actually by bringing the number down and teaching us about how exoplanets are destroyed and what that teaches us about the orbital dynamics of exoplanets. Okay, right. The next thing. So I was, just looking up the Caltech Astronomy website, and this was on the homepage. It's not surprising. SphereX is launching this week, as far as I'm aware. And one of the key challenges in following up our sample of 5 million infrared transients. Remember, we've only probably followed up of the order of 100 of these. There are, 900,000 remaining to be followed up. And obviously that's something, the number is large enough that I don't think it's possible to do it, one by one. And this is why I'm really excited about SphereX, because SphereX will get spectra for us for essentially all of the things that WISE detects. So these are the sensitivity of SphereX that I got from get online. The magnitude as a function of wavelength. This is the WISE sensitivity. And you see that SphereX is really well matched to getting spectra of anything that's detected in WISE. So Viraj here, and if he's here, Viraj created this plot that showed the cumulative distribution of the number of transients we found in NEOWISE compared to the SphereX sensitivity. So here, this is the distribution of apparent magnitudes, total about, for the order of 100,000 transients, and basically all of them are going to be within the reach of SphereX for spectroscopy. So this is going to be a game changer when it comes to systematically probing this population of transients, which barely scratch the surface of. So again, this is not something I need to say here, but I'm involved in a number of ground-based infrared surveys where one of the challenges with NEOWISE was always that we were finding things 5 years after, because of the way the data is released, because it's very slow transients and it takes time to get these things identified from the data release schedule and everything. But I think in terms of following these up in real time, looking at the outbursts as they are emerging, this is something that's going to become possible with these ground-based infrared surveyors. And I'm currently involved with 2 of these experiments, Winter, which was being built at MIT when I was there, and Prime, which is a new infrared camera in South Africa. That's also going to do primarily a survey of the galactic bulge, but also other regions of the sky. And we have a real-time pipeline running, looking for infrared transients in these data sets. And finally, Roman. Yes, Roman is coming. One of the things I'm really excited about is this idea that Roman is going to do a galactic plane survey that's been decided. It's about 700 hours of Roman time that's been dedicated to a galactic plane survey. And the reason, even though this is going to be mostly a static survey, the reason I'm excited is because it really simplifies the connection in going from the very faint progenitors of galactic transients that we barely detect in traditional surveys to actually connecting them to their outbursts. Usually the way we actually did it for the planet engulfment event is that it's a huge, this is a very crowded field in the galactic plane where you see a transient, and you have to go get follow-up imaging with adaptive optics to see what the transient progenitor was and establish the nature of the star, that it was a subgiant and so on. But this becomes essentially routine once the Roman Galactic Plane Survey becomes available. Something like LSST or ZTF finds these transients, we immediately know where to look and for the progenitor in these things. And this is something that we are trying to push very hard with the Galactic Plane Survey. And this is it's part of a committee that we are optimizing the galactic plane science for a lot of different things. So yeah, so that's it. These I'll leave you with this. What NEOWISE images actually look like when you look for the transients. These are transients that are appearing. But probably my favorite animation in this is that, and keep an eye on this. This is the M31 object. You can see a black hole forming in real time as the star disappears away. Thank you. You mean for the stellar mergers? Yeah, yes. So this would be essentially very close to the dust condensation radius for the outburst itself. So there is the outflow that's escaping from the merger remnant, and at some distance it cools enough to form dust and then enshrouds the central remnant that's inside. No. For the mergers, the stars usually themselves are initially hot enough. Like they're probably not dusty themselves initially, but they can become very dust obscured because of the outflow that escapes. And at some point, it just reaches a radius where it's cool enough to form dust. New dust formation. Yes, the extinction from the new dust formation. And this appears to be ubiquitous in any type of stellar merger that we see. Yes. So what we see is that when the optical disappears is also when the infrared brightens up. So yeah, so bolometrically the source doesn't fade that much. So if you were able to measure the bolometric output of a red nova, it's fairly slow. It's like has some power law that's slow. But in the optical, it's much more dramatic because all of that energy is being blocked by the dust and re-radiated at longer wavelengths, which is mid-infrared. Yes. Yes, that's a good question. I think for the most part, because of the limited amount of data, we assume a spherical geometry for these shells. But if you look at galactic stellar merger remnants, there is clear evidence that there are bipolar outflows in the sense that the most of the material, the dust is likely formed in the orbital plane where the most of the mass is ejected. But those kind of geometric studies are usually just possible for the galactic events, which there are about 5 of them known in the Milky Way. Yeah. Yeah, so I think the velocity of the CSM it's trickier because so I think we haven't done this specific measurement, but I think the only way to do that is that when you get a late time optical spectrum, you can measure what the width of that narrow component is, and presumably that likely reflects some kind of wind velocity for this material. But I think it's a bit more complicated because electron scattering can produce all kinds of Lorentzian profiles. So I don't think it's that straightforward. Yeah, but I think spectroscopy, yes. Right. So I mean, I think the 1,000 years number, yes, comes from the time for the infrared brightening. So if it happens after 1,000 days, 10,000 kilometers per second. So we have a distance. But yes, depending on what you assume that velocity could be 1,000, maybe 10,000, maybe 100. Yes. 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 So yes, that's a good point. This is something that Jacob and I have thought about it. So one of the most notorious contaminants in galactic plane searches is the region around Cassia, because Cassia has this huge series of dust echoes around it. And so even though it's optimized, so even if you have an extended structure, if it's bright enough, it's going to show up as sufficiently bright point source at some point if it's bright enough. So we do see a number of that. So we have an effort. So because those are contaminants for point sources, we have an effort right now with Ashish, who's I think not here, but so Ashish and we are working on this a project that we take these cutouts from these difference images and do a machine learning classifier to classify the point sources as opposed to the extended sources, which both helps us point sources and finds the dust echoes that I can send to Jacob for follow-up. Yes. The pipeline looks at both. I only look at the things that matter. Yes. Yes. As you know, so I think the ZTF folks know here, which is things that fade. ZTF produces negative alerts. I just haven't seen anything done with the negative alerts. But yes, it's so I think the negative alerts are dominated by things like high proper motion stars, because when a star moves, it produces a negative alert. Yeah, I think so. I did look at it once. I just remember there's all proper motion stars in some form or the other. Yes. Yes, yes. Yeah. So any regular variable, usually, I mean, with the NEOWISE cadence, you don't see a lot of variables. 6 months is a very long time. But yes, those like YSOs, for example, they show all kinds of brightening and fading events. Yes.
It's just that the black hole formation event at the percent of
Yes. So because this is M31, you go very deep with HST imaging, and there's no evidence at that position for even something like a sun-like star. It's just not there. So the likely explanation is wind mass loss. And so for the models that Morgan was doing, we essentially just cranked up in MESA, cranked up the wind mass loss at the end of its life to produce this roughly over a few tenths of a solar mass of hydrogen. But you're right in that we don't see evidence of a companion, at least because it's M31 again.
Okay.